Thank you. Yeah, I'd really like to thank organizer for organizing such a wonderful program and the conference. It's really very timely. Today I'm going to talk about this generalized symmetry and gapless states. The take-home message is that the gapless liquid actually is a number theoretical problem. So, because of this topology order and this long-range entanglement, now we have very systematic understanding of a gapped phase of matter, a gapped liquid. So in terms of this tensor category theory. And so recently we just have classified the modular tensor category up to 12 anyons, which is basically classified 2 + 1 dimensional gapped liquid phase. So, so after this understanding of a gapped phase, so next challenge is a gapless state. So can we get a systematic understanding of a gapless state? But here gapless, I mean the strongly correlated gapless states, which may not have quasi-particle, and whether there's a way to have some breakthrough here. One idea is that using the emerging symmetry. We know the gapless states always have an emerging symmetry. And recently we find the emerging symmetry can be group-like, anomalous, higher form, higher group, non-invertible, and algebraic, and all these very rich, a lot of emerging symmetry. So because emerging symmetry became so rich, so it became brave. That is maybe emerging symmetry completely characterizes gapless states. So if that's true, a gapless liquid, I mean, if that's true, we can ignore the quasi-particle, all this field theory. We just study the emergent symmetry. So emergent symmetry carry all the information about the gapless states, like a scaling dimension and all other critical properties. So then this study of a gapless state became algebraic or maybe number theoretical problem of study this emergent symmetry. So now from this point of view, we see that it's very important to have a very general theory which cover all those emergent symmetry in a uniform framework. So certainly this general theory for emergent symmetry or generalized symmetry is not group. It's not even higher group. That's not enough. We need something even more general. And so our attempt to develop a general, so there's many different approach to develop this general theory. And so here I just list the currently known all different approach and some reference here. And so for our approach, actually we start with our approach starts from this study of a gravitational anomaly. So in 2014 and 2015, we want to develop a theory of which classify all the gravitational anomaly. And here we kind of redefine what is a gravitational anomaly, not the one defined by energy theory. So we define gravitational anomaly as the obstruction to put a field theory on lattice. You know, when we have field theory, that means the theory is locally consistent, something nice. But however, this locally consistent field theory may still be wrong. Maybe there's obstruction to put the field theory on lattice, and we call such obstruction a gravitational anomaly. And then we realized that we can always put the field theory on the boundary of a lattice model in one higher dimension. Okay, and so therefore, from this point of view, we find that actually the gravitational anomaly in the field theory corresponds to topology order in one higher dimension. If this one higher dimensional lattice theory have a trivial order, then the theory can be put on the lattice without going to one higher dimension. However, if this bulk lattice model have a non-trivial topology order, that represents obstruction to put the field theory on the lattice in the same dimension, so that's a gravitational anomaly. Okay. So so then we study as an application of a gravitational anomaly. Then we study so-called morphism between quantum field theory. Certainly, this is my my collaborators' motivation. I don't care about the morphism in quantum field theory, but now I realize I should care. The reason is that morphism or homomorphism is a very, very important mathematical concept. It's a map between two objects preserving structures. So actually, maybe this is the most important mathematical concept in mathematics. Everything is some kind of homomorphism. So if you want to understand the quantum field theory, so morphism between quantum field theory should be very important. So physically, how we define the morphism between quantum field theory? So I translate into physical language. This so-called morphism actually, at the moment, we review this as so-called local low energy equivalence. We say two quantum field theory, if they're local low energy equivalent, we say, oh, they are maybe related by morphism. But what we mean by local low energy equivalence? So one idea is that we have quantum field theory, we stuck with some gapped state. Another quantum field theory stuck with another gap state. If after stacking, these two theories become identical, then we say the original two quantum field theory will be local low energy equivalent. So this is just a very rough idea. Then we can make this idea more general. In a sense, we can have an anomalous quantum field theory. That means it's a boundary of a bulk topology order. So this blue region means a topology order. And we have then this boundary have this decomposition. This decomposition means that this stacking of this top boundary and another topology order and the lower boundary, this composite object or composite system is identical to this original system. Means they have same low energy spectrum, same partition function. So if this quantum field theory allow this isomorphic decomposition, and then we say that there is a homomorphism between these two quantum field theory. So this is a very abstract application of a gravitational anomaly. Yes.
Can I just ask? So these statements are in the IR.
Yes, in the IR. Yeah. So in a sense, so these two quantum field theory we have low energy extension, but the bulk and the top boundary provide some grounded density, some sector. That's also low energy, but not like quasi-particle like excitation. So this top boundary and the bulk providing some additional sectors, but the local low energy, like a correlation function with local operators, they are all captured by these two lower boundaries. So that is the idea. And so with this idea, then we can say that these two quantum field theory, both are anomalous, are kind of a local low energy equivalent. Or mathematically, we say that there's a homomorphism between two quantum field theories. So it's kind of some abstract study. Yeah. Yes?
So do you require the junction to be topological?
Yeah, this junction is a transparent domain wall, and this one is a topological boundary. But on the other hand, I want to de-emphasize the topological. I really means they are gapped. When I emphasize topological, there are certain homomorphism in topological quantum field theory that will become a symmetry. But however, when I emphasize topology order as a gapped, the homomorphism may not be a symmetry because those gapped anion may have different mass gap, different gap. So there may not be symmetry. This is turned to be important. Yeah. So this is just a study of some gravitational anomaly. Seems kind of abstract. It's a kind of useless thing to do. And but a few years later, we realized that actually gravitational anomaly is a symmetry. Yeah. So therefore, the previous transparency, this study of a gravitational anomaly and homomorphism, actually is a theory of a generalized symmetry. So when I first read on the paper, we didn't realize that, but only a few years later, we realized that one actually is a symmetry. So why gravitational anomaly is a symmetry? One way to understand is following. We can consider a symmetric system, but restrict ourselves to the symmetric sub-Hilbert space. When you do such restriction, you find you are in a very strange situation. That is, the symmetry action became trivial. within the symmetric subhilbert space. Means when you do this such restriction, you no longer have a symmetry. You don't have a symmetry transformation that trivially. Then we know from experience that even when we restrict to symmetric subhilbert space, the symmetry is still there. The low energy dynamics still constrained by symmetry, even though we lost the symmetry transformation. So the question became, how do we recover symmetry in such a situation? Okay. One way to recover symmetry in such a situation is that we notice that the symmetric subhilbert space do not have a tensor product expansion, decomposition, because we restrict to the charge zero sector. And lacking of tensor product decomposition is a gravitational anomaly. So actually, when you have a field theory which do not have a tensor product decomposition, that means you cannot put that on a lattice. So this is a very rough but a very direct way to see that symmetry and the gravitational anomaly are directly related. Okay. There's other way, but this may be the quickest way to see that. Yes.
Is the inability to put the theory on a lattice of gravitational anomaly statement, is that equivalent? Is there a way to state it in terms of tooth anomaly or not? Like
not tooth. Tooth anomaly by definition is a symmetry anomaly. This is a gravitational anomaly. So so from kinesimetric language is that the gravitational anomaly really means that at least it means that the Hilbert space do not have a tensor product decomposition. So I feel this maybe can be used as a definition of a gravitational anomaly, very direct. Tooth anomaly is about the symmetry. Yeah.
Symmetry engaging inability.
Yeah, the inverted gauge or maybe symmetry anomaly is something about the symmetry. Yeah, this is have no symmetry. Once you restrict to symmetric subhilbert space, there's no symmetry. Yeah, yeah. And so the slogan is that the symmetry actually is a non-invertible gravitational anomaly, and non-invertible gravitational anomaly is a topology order in one higher dimension. So the message is that the generalized symmetry is not described by group, but described by topology order in one higher dimension. So that is the general theory for the generalized symmetry. And so more specifically, so let's go back to this wedge picture. So using this symmetry language, so we see that we originally have a quantum field theory with a symmetry, but this symmetry is hidden. We don't know. It's not exposed. However, if this quantum field theory have this kind of decomposition, have an anomalous quantum field theory, have a topological bulk, have another topological boundary, if they have this decomposition, then this decomposition reveal that this original quantum field theory have a symmetry. So such decomposition expose the symmetry. So that's a key message. For example, if this quantum field theory have a group-like symmetry, like a G symmetry, then it will admit a decomposition like the bulk is a G gauge theory, and the top boundary is this gauge charge condensed boundary. And so this is a way to expose symmetry in your theory. And that is this point of view is very general. So under this point of view, we don't care about the anomalous symmetry, non-invertible symmetry, higher form symmetry. They're just all these topological symmetry topology order. They all unify together. One don't have to distinguish those anomalies. So actually, after this understanding, I try to not talk about the anomaly. So then we call this a bulk. This bulk topology order is called the symmetry topology order, or SymTO. And this yeah. So this is a picture for the symmetry topology order. Yeah. And so that may sound a little bit abstract. So let's put this data in a more concrete setting, physically. So a system with a symmetry, when restricted to this symmetric subspace, can be exactly simulated by the boundary of the corresponding symmetry topology order. So therefore, whenever you want to study a system with a symmetry, you just find the corresponding symmetry topology order and study their boundary. Certainly, a system with a symmetry is not unique. There's many systems with the same symmetry. But the boundary of topological order also not unique. There's many different boundary. The claim is that there's a one-to-one correspondence between the symmetric system and the boundary of symmetry topological order, such that the low energy spectrum of the two systems are identical. But for symmetric system, when I say low energy spectrum, I mean the spectrum within this symmetric subspace. And so this is exact complete simulation. So using this idea, so we can study any symmetric system, the low energy dynamics, by studying boundary of a symmetry TO. So that's how we use this kind of a holographic picture to study symmetry and to study gapless system. I just want to mention that originally this symmetry TO is called the categorical symmetry. You know, at that time, actually I did a search. There's another similar name called the fusion category symmetry. So I thought the categorical symmetry and the fusion category symmetry is different. So maybe it's okay, no confusion. But unfortunately, it's no. And so the fusion category symmetry was later used by people refer to as a categorical symmetry, which is different. And so this caused a lot of confusion. So we have to change our names. So now we call the symmetry, categorical symmetry, as a symmetry TO or symmetry TFT. Yeah. So so now this the main topic of this talk is that how we use symmetry topological order to determine the gapless or gapped state. You know, that's a main thing. And the idea is that we want to study the boundary of a topological order. And however, the boundary of topological order is described by a partition function, which is not a value, it's a vector value. It has several components. Okay. So actually we have this vector value partition function with many components. And each component actually is labeled by the anyang in the bulk. So you have 10 anyang in the bulk, the boundary partition function would have 10 components. Okay. And then this boundary partition function and the bulk topological order are related by this modular transformation. So under this modular transformation of this tau is a shape of a boundary, a 1+1 dimensional boundary. And under modular transformation, this vector value of the partition function transform using this ST matrix. And the ST matrix is some modular matrix characterizing bulk topological order. So this is really generalized this standard modular bootstrap, which says that the gapless system in 1 dimension, 1+1 dimension, have a modular invariant partition function. And we generalize that into modular covariant partition function. And this modular covariance is determined by this bulk topological order. That's a symmetry input. So basically, if you know the symmetry, you solve this equation, you can obtain this boundary partition function, then you can obtain the boundary gapless theory. So that's how the symmetry constrain the gapless phase or gapped phase. So basically that's a program. So that's what I refer as a number theoretical problem. Solving this equation actually is a number theoretical problem. So let's give some example. Like for the Z2 symmetry, the bulk topological order is Z2 gauge theory. And this ST matrix is given by this 4x4 matrix. And then here we ask what kind of gapped phase is allowed for the Z2 symmetric system. The gapped phase described by boundary partition function, which is trivial, because gapped phase is a trivial CFT. So boundary partition function is just a constant, which actually is a non-negative integer. So we need to find a non-negative integer solution of this condition. This T and the S matrix is given by this, and the Z is a four-dimensional integer valued vector. Just finding the solution, then we have these two solutions to satisfy this condition, and one condition corresponds to this E anyang condense, because this element is correspond to E anyang in the bulk. So if a boundary partition function is not, if this E anyang component is non-zero, that means we can create a pair of E anyang. So there's E anyang in the bulk, and another E anyang would condense to the boundary. So even when boundary have E anyang, the partition function still non-zero, means still ground state, and that means the boundary can absorb E anion without changing its energy. So this really means the identity anion condense, that's always condensed, but the E anion also condensed. And this one corresponds to Z2 symmetry breaking states. Then another boundary is this M anion in the bulk condensed. So that corresponds to Z2 symmetric phase. Okay. So from here we can see that by simply solving this RGB equation, we can obtain the gap state. I want to mention that this method even works to get SPD state. For Z2 symmetry in 1+1 dimension, there's no SPD state, so we just get a 2 symmetry breaking state. But for Z2 cross Z2 symmetry, this method will also give us SPD states. Then next thing we can try to find out what kind of gapless state we can obtain for the Z2 symmetric system. So here we ask the following question: whether a Z2 symmetric system have a gapless state described by this Ising conformal field theory. Okay, so then we just using this Ising conformal field theory character and try to find this partition function which have a tau dependence and satisfy this condition. Okay, and so we have a program to do that, and we find this kind of combination of Ising character would satisfy that condition. So that's one solution. And in this solution, if you look at this Z1, the first component, you see this first component contains this chi0. Chi0 is a conformal character for the primary field. And this chi1/2 is a conformal character for this primary field with scaling dimension 1/2. So this 0 appear here, that means that's one condensed. This 1/2 appear here, the scaling dimension, total scaling dimension here is a 1. So this one is a relevant operator. So this means there's a symmetric relevant perturbation in this gapless phase. So therefore, this particular gap phase is a gapless phase with relevant perturbation. Yeah. Yeah, this is a necessary condition. Yeah. So there's many solutions. Yeah. Oh yeah. Yeah, totally right. The solution we have, if you only solve this condition, you may get a fake solution, which is invalid. But actually, there are some additional conditions. But at the moment, even with this additional condition, it's still necessary, not sufficient. And it's an open question: what is a practical sufficient condition we can use? Yeah.
Is there something special about the solutions that, like disease, that satisfy this condition, but are yet not?
They're just invalid.
So can you repeat the question?
Yeah, I think the question is that suppose you find a solution of this equation, and later turn out this solution is fake. They actually do not correspond to a valid gap state. That's possible. And I would say they just a fake. And the reason is that this condition is only condition on the torus. We should have a modular mapping class group on the genus 2 Riemann surface, genus 3 Riemann surface. There are similar conditions on those high-D Riemann surface. So when they're all satisfied, that may be sufficient. Certainly we're not sure, but that may be more sufficient. Yeah. So that's a very good question, but that's open question, open issue. And we really, but at the moment we don't have too much. So this turned to be pretty effective. So, but indeed there's danger we may have fake solutions. Yes.
Just a quick follow-up. So finding the algebra, condensable algebra in the bulk, finding the condensable algebra in the bulk, isn't that the solution, or you think?
Yeah, it is a solution. So actually this solution have a condensed algebra of 1. So this, maybe let me say. So this actually condensed algebra. So this is just 1 and E condensed, or this 1 M condensed. And when those condense, you break symmetry completely, you get the gap states. Then the transition between these two gap states is given by the overlap of these two condensed algebra, which is identity. So this is so we have a smaller condensed algebra, which do not break CMTO completely. And those kind of smaller condensed algebra give rise to gapless states, unlike this one. So this one happened to be a transition point between these two gap states. So therefore, the relation between condensed algebra tell you the phase diagram. So which is a phase, which is transition, you know. And certainly the solution is very general. It also have this kind of another solution is this 5-4 minimum model, which happen to be a multi-critical point. Yeah. And then we can apply this to the S3 symmetry. For S3 symmetry, the bulk is S3 gauge theory. So CMTO is S3 gauge theory. And to study the gap phase of S3 symmetric spin chain, you just want to find all the maximal condensed algebra which break the CMTO completely. So those are onion labels, 1, A1, A2, that's a 1D representation, 2D representation, those are a flux, and the bound state between charge and the flux, etc. So this 4 corner representing 4 different condensed algebra which break CMTO completely. They give rise to gap states, which correspond to S3 symmetric phase, Z2 symmetric phase, Z3 symmetric phase, and Z1 symmetric phase. Z1 symmetric phase means S3 is completely broken down to Z1 symmetry. And then the overlap of those two condensed algebra, in this case like 1 plus B, that's also another condensed algebra, that's a gapless states. And from this gapless state, we find that the critical point is a 4-3 minimum model, which is the Ising. So therefore, this transition between S3 and Z3 is Ising critical point. And interestingly, that between S3 and Z2 phase, we only have this minimal condensed algebra. So this is this condensed algebra. And for this condensed algebra, there is several candidate critical point. So the 6-5 minimum model have 1 relevant operator, and the 7-6 have 2 relevant operator, and the O2 CFT also have, O2 means orbifold CFT, also have a 1 relevant operator. So in principle, the critical point between this S3 phase and Z2 phase, that's a pulse transition, could be this 6-5 minimum model, or could be this orbifold CFT. But numerically, we find it is a 6-5 minimum model. And so this is a way we can use this idea. And then however, this CMTO give us something new, because this Z3 S3 gauge theory have automorphism. If you exchange this A2 and B, it's automorphism. So this automorphism means that this phase diagram have this it's not symmetry. Have this automorphism means that if you exchange S3 phase and Z2 phase, or Z3 phase and Z1 phase, basically if you do the reflection on the vertical line, the whole thing should be the same. So that really means the critical point have relations. The interesting is that in another phase diagram, we see that there is an S3 to Z1 transition, direct transition. And the automorphism, this transition map to this Z2 to Z3 transition, one of Landau forbidden transition. So this automorphism really says that the S3 to Z1 transition is the same as a Z2 to Z3 transition. They gave by the same critical point. Yeah. But which critical point? At the moment, our guess is this is a Z2 orbifold theory. Yeah. That is a Z2 critical point. And so this is I already remarked that there's a slight difference between CMTO and CMTFT, because automorphism in the onion data is a symmetry in the CMTFT, but it's not a symmetry in the CMTO. So therefore, the boundary of the CMTO may not have this automorphism symmetry. But on the other hand, if a CMTO have this automorphism, that means you can fine-tune the bulk topology order to make this automorphism actual symmetry in the bulk. And then you can also have a boundary which respects the symmetry. So therefore, this automorphism can become a symmetry. So this actually corresponds to the self-dual S3 symmetric model. So S3 symmetric model have a duality transformation, and there's a self-dual point. and representing this, having this automorphism symmetry. Okay. And so therefore this self-dual, this additional automorphic symmetry is a non-invertible symmetry. It's a duality symmetry. And that's a symmetry, additional symmetry for this self-dual model. And so what is SymTO for this self-dual model? It turns out that SymTO for the self-dual model is this JK4 times JK4 bar topological order, some kind of weird topological order. And then from using this condenser algebra, we can study all their gapped phase. So there are only two maximum condenser algebra. So this phase, this self-dual S3 model, self-dual S3 model only have two gapped phase. And both gapped phase have a non-trivial ground degeneracy. There is no gapped non-degenerate phase. That means this self-dual, the symmetry in the self-dual S3 model is anomalous. This non-invertible symmetry is anomalous. There's no gapped non-degenerate phase. And there's also those are kind of non-maximum condenser algebra. And especially you find we can obtain the gapless phase. In particular, there's a 6-5 minute model, and they have no relevant operator, so they are gapless phase. So in the self-dual self-dual S3 model have a gapless phase. So this is one phase diagram. So this is one gapless phase with center charge 0.8 for right mover, another 0.8 for right mover. They're same. And there's continuous transition, center charge 1.3, I think. And also there's an incommensurate phase here, and there's a transition. I think this transition probably is equal to 2 transition. And but they are all gapless phase for this S3 self-dual model. But using this SymTO, we can have some understanding of this phase diagram. Yeah. Thank you. I think that's my talk. Yeah.
Yeah, I have a couple of questions. So in 1+1D gapless phases, can you describe like non-rational CFTs or something that's, large central charge CFTs? Is that compatible with your framework?
Yes. And but also that's a more difficult question. Okay. So far when I talk about SymTO and the symmetry, I mainly concentrate on the finite symmetry. So when we have finite symmetry, the story is much more complete. And when we have a continuous symmetry, then the bulk topology order will have an infinite number of anions, which happen to be the mathematical theory is not fully developed. Some kind of category theory with infinite number of anions. Yeah. And it's so we need that to be developed. And so actually for the continuous symmetry, there are difficulties, but I believe things still work. But when we have the non-rational CFT, usually there's a continuous symmetry involved. And but that's also very interesting. That means continuous symmetry have an extra feature there. The story I described is too simple. And but when you have continuous symmetry, there's an additional feature. If you bring that additional feature, maybe you can address your question more satisfactorily. Yeah.
I mean, I had in mind CFTs that are, chaotic, that have near maximal chaos, and those, I don't know whether they will fit into this framework. The other question was, suppose I go to 2+1 dimensional gapless phases, how about just a free Fermi surface?
Yeah.
What is the gravitational anomaly
of that? Very good question. You can see when I say the slogan of this talk is a gapless liquid is a number theoretical problem. So that means a liquid. The liquid really means that it's not a Fermi liquid. So Fermi liquid is not liquid. That's a point. So actually, Fermi liquid corresponds to this very particular incommensurable phase because of this 2kF have different values. So it's a much more exotic phase. And so more like a fracton. So at the moment, this kind of framework do not directly apply to fracton or directly apply to Fermi liquid. So one need another version. Or let me put it this way. If you have this kind of theory, holograph theory, to describe a gapped fracton phase, and that kind of theory would be more suitable to describe a gapless Fermi liquid. So Fermi liquid belong to that kind of a theory. And the theory I described so far is more like an ordinary critical point, like a Dirac point, maybe it's okay. So those are maybe closer to the gapped liquid phase. Yeah. Yeah.
Yeah. So just to follow up on that, do you expect, for example, free boson chiral CFTs with different Luttinger parameters to be in the same class or different classes?
Okay, yeah. You know, we have chiral CFT, and yeah, that's also a very good question. So maybe let me go back to this a little bit. You can see here we have this something with a symmetry. Okay, then we say they have this kind of decomposition. But notice that this bulk topology order have this gapped boundary. So that's one of the limitation. That means we are consider a symmetry whose bulk CMTO allow gapped boundary. However, we have a chiral boson theory. It also have a bulk topology order. But that topology order do not allow gapped boundary. And yeah, then I don't know what to do, you know. But this is definition, it's not a physics problem, it's a really definition problem. Should we include this kind of CMTO, this bulk topology order as CMTO or not? Then at the moment, the standard definition is that the CMTO is a topology order which allow gapped boundary. If a topology order do not allow gap boundary, we say that is illegal. That's not CMTO. But on the other hand, the situation described is very valid, very natural. So we feel we should allow the bulk topology order which do not allow gap boundary as also valid CMTO because that's determine the boundary linear dynamics. So I think this this kind of this still correct. This still works. Yeah. And actually, I personally would want to generalize the CMTO even further, including this chiral case. But the standard theory at the moment do not allow that. Yeah.
Thank you.
Other questions?
In the beginning of the talk, so you said that so symmetry largely determines the theory. So yeah, I wonder whether so in your framework, so in some explicit C-1 boson case, so the symmetry can determine so C-1 boson have different radius. And some point corresponds to some rational CFTs.
Yeah.
So I wonder whether so using your description, so we can characterize all all the rational point only using symmetries.
Yeah. Thank you for the question. And so I have to say that yeah, this conjecture is I don't know what to say. Maybe you can say it's a wishful thinking at the moment. Mm-hmm. And because you know, I really like to have a general understanding of a gapless theory, and I don't know where to start, so I just make a very bold conjecture. Mm-hmm. But the expert in conformal field theory don't agree with me. Well, there's a lot of counterexample, and this C=1 conformal field theory is one because they have the radius can be changed continuously. There's irrational CFT. This thing doesn't fit this conjecture. Indeed, it does not really fit. But however, I want to say the following: for this C=1 CFT with some irrational radius, there's also neighboring rational radius. Okay. And then for this neighboring rational radius, and you have this this kind of description would work. Yeah. And this rational radius will be dense on this axis. So that's my way to bypass this. Instead, what I try to say is that I don't start the irrational CFT, but I approaching irrational CFT using rational one, try to take a limit approaching that.
Yeah, take
That's
linear.
that's one. Another thing, another related is related to the Sibir's question. In this case, there's an emergence U1 symmetry. So this is a issue about continuous symmetry, because we don't have a theory for continuous symmetry. We only have a theory for finite symmetry. So because of that, so we have to do this weird way to approach, using rational point to approaching the irrational point. And so this is also the general way to define the continuous symmetry, because for continuous symmetry, there's a lot of subgroup. Then we try to say the collection for all the subgroup and the collection of all the finite subgroup, and the CMTO for this finite subgroup, this all the collection of CMTO may contain enough information to actually describe this continuous symmetry. So we're really using the rational point and try to take a limit to approaching the irrational point. So this, at the moment, this is what we have. Certainly, I wish there's a direct theory for continuous symmetry. But this point of view gives you some feeling that if you do have a direct theory, this direct theory what should they cover? They should cover this limiting case of a rational theory. And so basically, you will get irrational theory in the theory directly. But at the moment, we don't have this kind of a Brady diffusion category. So actually, the Brady diffusion category with infinite object should cover irrational case. And so there's some big change here. Yeah.
Yeah. Thank you.
Right. So let's look at the example with Z2 symmetry. So for example, the 2+1 the icing critical point and 2+1 the tricritical icing. So these two are different CFTs. So I wonder whether they have the same or different maximal emergent generalized symmetries.
Yeah, I don't know. Yeah, this is the key point is following. Thank you for the question. Usually when we describe a critical point or multi-critical point using the symmetry we know. But actually, when you actually have a critical point, the critical point usually have a more symmetry than your starting symmetry.
Sure.
So the key point is that to identify all the actual symmetry. Then after you identify all the actual symmetry, then there's maybe a hope this maximum emergent symmetry may fully characterize the phase.
That's why I specify 2+1D, because we know 1+1D, the tricritical icing has a lot more symmetries than the icing. But in 2+1D, I really cannot think of any extra symmetries actually.
Yeah, that's I don't know. Yeah, that's so basically, maybe let me turn it around. You say, so we want to start a 2+1 critical point. Then I'll try to say the key to identify this actual symmetry. And so what is this actual symmetry? So actually, like for example, there's an icing critical point. We say it have a Z2 symmetry coming from this charge conservation. It has an additional Z2 symmetry coming from the symmetry defect conservation. It have yet another Z2 symmetry from the EM exchange symmetry. So actually, the emergent symmetry of an icing critical point is a double icing topological order in one higher dimension. So indeed, I don't know the answer to your question. Yeah. So but certainly this in 1+1D, I have to say that in 1+1D the story seems okay, but 2+1D we really have too few example to check it non-trivially. So I'm not that confident in higher dimension. Yeah. Maybe there's some important thing missing. Yeah, that will, I don't know. Yeah, that's make the future research. Yeah.
Okay, one last quick question.
So if you just look at the C equals 1 bosons again, convex bosons. So when you tune the radius, in general, each different convex boson will have different, if considers a full set of symmetries, different symmetries.
Yeah.
So you can do T-dualities to relate some radii, and they all have the same symmetries. But do you know two compact bosons that are not related by T-dualities that have exactly the same symmetries, and you can consider all symmetries? In other words, like, you know, this conjecture, like, we just look at C equals 1, 2 bosons. Maybe it's true if we
yeah, the thing that I think for any rational point, there's a maximum CTO. But actually, in this case, let me put it this way. Now I realize that. But actually, the maximum CTO is a lot actually, yeah. And so I think in this paper we discussed a little bit, and actually for any rational point you can discuss the compatible CTO, and you find it's not unique. There's many CTO which admit the same boundary. And so that means there's a sequence of CMTO go to infinity. So that's compatible. Actually, there's an emergent continuous symmetry. Yeah. Yeah, this happened to be the tricky case. Yeah, because it's involving emergent continuous symmetry. So how to make a story perfect? Yeah, there's still open. Yeah.